everyone. In today's class on advanced characterization technique, we are going to talk about a new characterization technique known as grazing incidence small angle X-ray scattering. In the last class, we had studied small angle X-ray scattering, and we understood that how small angle scattering can help us about the distribution of sizes as well as shape of different particles and precipitates in a variety of materials. We also know that with the increase in research going on in nanotechnology, there is a lot of need for a characterization technique that can be used to characterize small scale sizes and shapes on the surface, right? And for that, we need to use a technique which is essentially known as grazing incidence small angle X-ray scattering. Now, if you remember, we had talked about grazing incidence while we talked about normal X-ray diffraction. So, we can have either a normal incidence wherein the X-ray beam is incident on your sample in a reflection or in the transmission mode, while in case of grazing incidence, the beam is almost parallel and makes a very small angle with the sample under consideration. The most important point that I would like to emphasize here onwards, and that is why I am sticking on this particular slide, is that what all techniques we are going to talk from here on in the course of this lectures is that are pretty sophisticated techniques, and these are not the techniques which essentially are available in laboratory, and like you just pick up your sample and take your sample over there to do the characterization. Instead, these are very sophisticated techniques, and it is expected that you understand these techniques and get exposure to these techniques, and then carry out your preliminary characterization using laboratory scale X-ray diffraction and other characterization tools, and then you go to these advanced characterization techniques in order to solve your problem of importance. So, let us start talking about grazing incidence small angle scattering in the present class. So, as I had already mentioned, grazing incidence small angle X-ray scattering is a variant of small angle X-ray scattering, but it is used extensively for carrying out characterization on the surface. It was developed by Levin et al. In 1989. So, you can realize that this technique is not something that is pretty old. In fact, there have been less than 15 years this technique has evolved. However, the development in this technique has been tremendous in the last 15 odd years, and this technique is used extensively in almost all synchrotron sources all over the world, because it is essentially applicable to study polymer films, nanoparticles at interfaces, implanted systems, porous materials, and deposited, embedded or stacked semiconductor nanostructures. So, you can see the tremendous implication that GSAXS offers for characterization, not only pertaining to semiconductor materials characterization, but also for surface related issues like surface chemistry as well as catalysis. Another important aspect that has been investigated extensively using GSAXS has been quantum dots, which have been obtained by state of the art processing techniques like molecular beam epitaxy and liquid beam epitaxy. The most important part and the biggest advantage that GSAXS offers is that we can really monitor the evolution of size, shape and morphology, as well as the distribution on the plane, a 2D distribution while the deposition is occurring. So, this way it offers us a tool to constantly monitor the evolution of these nanoscopic structures and the ability to play with the processing parameters, or rather the deposition parameters, to control the size, shape and morphology of the quantum or rather the nanoscopic entities to be processed. So, not only does GSAXS provide information about the morphology, it also gives us information about the structure of the material. We will not be talking much about the structure part, but I am just trying to touch upon this aspect just to let you know that GSAXS can give us some information about the chemical structure as well as the morphological structure of the material. It gives us information in the same length scale as that of SAXS, ranging from about 10 to 1000 angstrom. In addition, it can give us information about in plane since grazing incidence X-ray, small angle X-ray scattering essentially is a surface characterization technique, it gives us information not only in the plane but also out of the plane or normal to the plane, which is very, very important for doing what is known as X-ray reflectivity. And like I had already mentioned in the last class, small angle X-ray scattering is complementary to say characterization techniques like SEM, TEM and atomic force microscopy. Similarly, GSAXS is also complementary to something like SEM and atomic force microscopy. At the same time, as we discussed in the last course or the last slide, we figure out that GSAXS is absolutely essential and absolutely state of the art when it comes to studying in situ studies on deposition of various materials. The best part about GSAXS is that simply by varying the probe depth, the depth to which the X-rays are penetrating, we can study subsurface information, we can obtain significantly important subsurface information using GSAXS. This is particularly important for studying subsurface damage caused during say something like implantation. The other important aspect which is very important, peculiar to GSAXS is the ability to study in situ deposition and catalysis. At the same time, like we had discussed in the last class, that small angle X-ray scattering also provides us, if not directly, in an indirect way, the chemical contrast between different phases. We can also use GSAXS and separate out chemically distinct entities in GSAXS. However, having said that, I hope you appreciate that in grazing incidence small angle X-ray scattering, the entire diffraction is occurring from a very, very small volume of material. And since the volume of material is very, very small, the kind of intensity that we are going to get is also going to be very, very low. And therefore, we need a synchrotron source which gives us very high brilliance and intensity to obtain good amount of data using grazing incidence small angle X-ray scattering. In the last class, we had discussed that for small angle scattering, a synchrotron is essentially good. But however, you can always do small angle X-ray scattering using say a rotating anode or a microfocus tube. However, in order to do grazing incidence small angle scattering, it is almost always better to use a synchrotron source, as the results obtained will be of high fidelity using a synchrotron source. So, let us first try to understand what exactly or how really it works out in case of grazing incidence diffraction. So, let us look at the grazing incidence geometry first. So, if you look at the grazing incidence geometry, here I have shown a thin film deposited over a substrate. Here you can see I have kind of exaggerated this incident angle, say theta I, and you can see how the incident beam on the substrate gets diffracted. At the same time, since it is incident on the sample at a very small angle, we do get a diffuse scattering or due to specular reflection, and this is, if you can imagine, it is going mostly perpendicular or at an angle away from the substrate plane. At the same time, we also have a refracted beam which is going over here. Now, I hope you appreciate, depending on the incident angle, we can have various situations. This is what is depicted in the next slide. Herein, it is shown that for a angle theta, incident angle theta, which is less than a particular critical value, which will be described in the next graph or next image, you see there is no refracted beam. At the same time, there is no beam along the surface. So, there is just an incident beam which just bounces off from the surface of the substrate. So, this is what happens below the critical limit, which is the theta critical or theta c in case of any substrate or any material. However, when you increase the theta incident, which is over here, you see that at a particular angle you do get a diffracted or reflected beam, but in addition to that you get another refracted beam which just travels parallel to the surface of the substrate. So, the angle at which this particular phenomena occurs is known as the critical angle. This essentially ensures that if your theta is less than theta c, you do not get any beam that gets refracted. However, at theta equal to theta c, you do get a condition where your beam does not get refracted, but in fact it runs parallel to the substrate surface. Now you can imagine that if you are at theta equal to theta c, you are going to get some information of the surface, what all you are having on the surface. At the same time, when you have an angle which is more than theta, which is more than the critical angle, you do see that you do get a refracted beam also. So now you can imagine by just changing the incident angle, we can get a lot of information from the substrate. Imagine now, let us go to the previous slide and look at a realistic situation wherein we not only have a substrate, but also we have a thin film, or say something like a quantum dots, different morphology, or say nanoparticles which are deposited on the surface of this substrate. So you can imagine that by choosing a proper combination or rather a proper value of theta, we can get different conditions and obtain a lot of information which is pertaining to within the surface or normal to the surface or subsurface in grazing incidence geometry. Now this particular point is exploited extensively while doing grazing incidence small angle X-ray scattering. So in this figure we have shown how exactly a thin film is deposited on a substrate, and how when a high intensity X-ray is incident at a particular angle, say alpha I, it gets reflected at a particular angle alpha f, which is not shown over here, but we will have a look at it later, and there is another angle omega, which is or rather xi, in which there is in plane diffraction, or rather in plane diffraction. So you can see that there is one condition where there is out of plane, and in the other case there is diffraction within the plane, which is along the direction parallel to the surface of the substrate, and therefore the scattering vector is given by q parallel, while the normal vector, the scattering vector in the direction normal to the substrate plane, is given by qz. Now how do we choose a critical angle for doing grazing incidence small angle X-ray scattering on a film deposit on a substrate? So I hope you appreciate that we can have two critical angles over here, one for your film or a nanoscopic particles that are deposited on the surface, and other for the substrate itself. So we choose depending on what kind of information we need. Obviously we are more interested when we are studying say a thin film or the nanoscopic deposited particles, we are more interested in these particles, and therefore we want all the information, the diffraction information from these particles. So we want that we do get some information from we get maximum information from these particles. Therefore I hope you appreciate that my theta has to be greater than the theta critical from theta critical of the particles or of the thin film. Now this is very essential to ensure that my X-rays get refracted. Let us go back to the previous slide and have a look. So if my film, if my theta is greater than theta c of the particles, this will ensure that my X-ray is passing through the particle, and this can give me a lot of information about the structure as well as morphology of the particles. However, or thin film for that matter. However, if my theta c is higher than that of the theta critical for substrate, then my information what I am getting for the nanoscopic entity, either a thin film or a particle, will also contain some information due to substrate diffraction. This is something that I want to avoid, since my area of interest is only the nanoscopic film or the particles. Therefore, I have to choose a critical angle for my thin film or nanoparticle on a substrate assembly, such that the angle lies in between the theta critical of the substrate and that of the film. Okay, so that I get some signal from the, or rather most of my signal is coming from the thin film, as well as I get some signal from the substrate, but there is no refraction occurring in the substrate. Now this is also very important if at all say I am doing implantation studies. You know what happens during implantation? During implantation we have heavy metal ions or heavy ions colliding with a with the substrate. So, you can imagine that there will be a lot of damage caused in the substrate depending on the energy of the ions, and this damage can vary depending on the depth, right, the distance from the surface. So, if you want to study the subsurface damage that is occurring due to implantation, you can always play with the incident angle, the theta, so that we get information from different depths. So, this is one parameter which is used routinely to control the information, the extent of information that we are getting during grazing incidence, small angle X-ray scattering. So, the entity that I was showing, like how exactly it looks. So, this time around I have drawn a set of a bunch of rather small nanoparticles on a substrate. So, we have the beam incident at alpha I and the wave vector corresponding to it at ki. This gets scattered at kf, the scattering vector is kf, while the angle here is alpha f. At the same time, this is normal, the scattering here is out of the plane. At the same time, there is going to be some scattering which is going to be in plane, and this is shown over here, which corresponds to this scattering vector qy and angle of 2 theta f, right. So, we have these two scattering vectors qz and qy, one out of the plane and qy which is in the plane, right. So, we get information, all the information related. So, you know that qy and qz will be in the reciprocal space, right, but qy will contain all the information corresponding to what is happening in the 2 dimensions, while qz or qz will consider all the information in the reciprocal space in the direction normal to the surface of the substrate. So, I have again another schematic which is shown over here, borrowed from a very nice review paper which I have extensively followed by Renowned et al. So, this shows essentially the realistic picture of what exactly is happening during GSAC. So, you have the incident beam and you see all these nanoscopic things, means we are really talking about very small dimensions. Means GSAC is used to essentially probe very small dimensions of the order of few nanometers. So, the structure is essentially similar to like this, and this essentially shows what kind of events that you can expect during GSACs and what kind of signals that you can get. Here again it is shown, you can see that this sample rotation is provided about omega just to improve the statistics, and this is how, and we can have note down the value over here, note down the pattern, the scattering pattern as a function of omega. Okay, so let us now go into and understand, try to just touch upon the physics of grazing incidence, small angle X-ray scattering. I would like to mention that it is a pretty involved subject, and I am not going to touch upon all the details of the scattering or diffraction theory associated with grazing incidence, small angle X-ray scattering. But what we are going to try and do is just to get a feel for things and see how the kind of knowledge that we have gained while deriving structure factor for normal diffraction, as well as we derived what are known as the form factors, right, in the last class, how these can be extended to understand how does grazing incidence small angle X-ray scattering works. So, you know that incident X-rays are at alpha I are scattered along kf in the direction 2 theta f and alpha f, right. Like if you go back to the previous slide, you see that there is this kf and there is 2 theta f, which is kf in the direction theta alpha f, and which is out of the plane, as well as in the plane it is reflected at 2 theta f, right. So, this is what is given over here. You can always define a corresponding scattering wave vector using the geometry as qxyz 2 pi by lambda and this particular matrix. Remember, this is in 3D. Now, if you remember, in small angle X-ray scattering we also had a term which was q, what we got was 4 pi by lambda, and there was a sin theta term, if I remember it correctly. Now, I hope you appreciate that we talked about this in small angle X-ray scattering, right. Like the angles we are talking about are going to be very small, and since the angles are going to be very small, in order to detect these very small angles, the sample to the detector distance has to be very large. Therefore, we looked that even in small angle X-ray scattering this distance was as large as 1 meter. Now, when we are talking about the grazing incidence scattering, the same rule applies, and we have a sample detector distance as large as 1 to 4 meters. So, this is quite huge. However, if you go to even what is known as grazing incidence, ultra small angle X-ray scattering, where the diffraction occurs at very small angle, less than certainly 1 degree, you see the distance can be as large as 1 to 12 meters. But this is only possible or rather only used when we are using a synchrotron light source. So, you know that the scattering intensity in the lateral direction, what all intensity that we are getting can be given is IQ, and this IQ is related to the form factor F, which is nothing but which carries the information of the shape of the sample in the reciprocal space, and your SQ, which is known as the interference function. This in fact is very similar to what we studied, what is known as structure factor. Now this I hope you appreciate and understand that here we are talking only about 2D structures. So what all structures we have in 2D, they can have lead to a particular structure factor, like we have for simple say FCC or BCC, you can do that, and in fact we will be going through one example over there. But the most important point is, so our SQ carries the information about the spatial distribution, right, while the F carries the information about the shape of the particles, right. So the actual intensity that we are getting is a combination of these two, and we know that this we had studied in the last class itself, that the shape function what we are having, so we can derive shape functions, take the Fourier transform, because remember what all in the real space what we are having, the particle or the particle or quantum dot for that matter is going to have a size, shape and morphology in real space. However, you have to appreciate that the entire information has to be mapped into the reciprocal space, and therefore we had studied that your reciprocal space is nothing but a Fourier transform of the real space, right. So all this shape, size and morphology are going to be modulated in a particular way to obtain a particular Fourier transform. So the size, shape and morphology that we see in the real space will be, if you take a Fourier transform of this size, shape, you can get a corresponding Fourier transform which corresponds to a particular size, shape of the particle in the reciprocal space. At the same time, when we talk about all these simple transformations, you have to keep one thing in mind, that one thing which you had taken for granted was that all this involved scattering only once, and that too kinematic scattering. So this is what is known as a Born approximation. However, I hope you appreciate that in GSACS geometry, the Born approximation may not hold true. Now let me just go back and tell you what exactly is Born approximation. So if you look at this particular image, you can see that you just have one condition. So there is one scattering right from one of these blocks or one of these dots of atoms or a cluster of atoms which we see over here. It can be a quantum dot or a nanoparticle. However, this is not the only case that can be expected. Like we can have a case wherein let us assume that if you are incident at a different angle, you get first reflected from the surface and then you bounce off and you go through this particle, right. There is a distinct probability of this happening. Let me just go and show you what exactly I mean. So if we go to the surface and we have say something like a pillar over here, in case of Born approximation, we know that there is only single scattering, while you know that in this kind of a case that is not necessarily true. So we can have a situation where your incident X-ray first gets reflected from the substrate and then it gets scattered, right. And I hope you appreciate that there can be a plenty of other options that can happen, right. Like it can go like this, get reflected, okay, or rather go, okay, I will just like to rub this off. I have made a mistake here. Okay, so let us go back and have a look what exactly can happen in this geometry. So this is something what we are having. So this is a substrate, right, and say this is something like a quantum dot. So the Born approximation essentially talks about single scattering event, right, single kinematic scattering. However, in this case, I hope you appreciate that we can have a situation where the beam gets first reflected, right, from the substrate, and then it gets scattered, or it can get scattered through this one, right, through your substrate, and then again get reflected, right. So, all these multiple scattering events can occur in the grazing incidence geometry. Therefore, we do not it is generally understood that this normal Born approximation of single scattering is not at all valid, and instead we do get different scattering events that lead to different scattering cross section, and therefore there is a need to account for all this in the calculation. Now, this is very complicated and I am not going to touch upon it, but this is what is known as, or these corrections considering all these events is accounted for in what is known as diffracted wave Born approximation, and it includes entire examples or entire category of reflection and refraction events that can be that can occur during grazing incidence small angle X-ray scattering. Right. So, let us again go back and look at the geometry. So, I see all the angles what we are talking about are pretty small, the alpha I, alpha C or alpha F are pretty small, but just for the sake of simplicity I have kind of blown them up so that we can appreciate it. So, you can imagine that what actually is happening, again the same image, that your sample incident, the X-rays are incident the wave vector kf, it is incident at ki rather incident at an angle alpha I. So, what we see is there is a specular peak, right. Now, the specular peak, as I hope you appreciate, gives you a lot of information in the, this is all along z, right. So, this is qz and this alpha f that you see, that is along qy. So, this gives you information about the in plane information, right, in the reciprocal space, while qz gives you out of plane, right. So, you get what is known as the specular peak. Now, this specular peak gives you the information which is normal to the surface of the substrate, right, or film. Therefore, it can give you information, and specular, as the name suggests, can give you information about, say, something like the thickness of the film, right, like, and this is classically known as X-ray reflectivity. While the second peak that you get is essentially what is known as the Yoneda peak, which gives you the maximum scattering in the z direction. Now, talking about specular peak, I hope you appreciate that in the form factors calculation we had seen that how we get a lot of bumps, right, like you get first a valley. Let me just go and draw it. Right. So, this is something what we had got earlier. So, this was I versus Q, and this was correlated with the size of the particle in our small angle X-ray scattering. Similarly, we can use the specular peak that we are getting to measure, say, something like the period, right, if you are having thin film, like what is the thickness of individual film. So, that information can be obtained using a specular peak. I will talk about in details in the next slide, but what I want you to remember is that the specular as well as the Yoneda peak, okay, which occur which show diffraction in the z direction, gives you a lot of information about in a direction perpendicular to the substrate of the film. Okay. So, in these specular peak there is no information on the lateral surface, there is only information for along the direction perpendicular to the plane of the substrate, and it is best to measure the average thickness of all the particles or average thickness of the film that we are having, and this gives rise to a technique known as X-ray reflectivity. However, I hope you appreciate that if you are interested only in obtaining information perpendicular to the direction or perpendicular to the plane of the substrate, you do not really want any information about the plane of the surface and therefore the plane of the substrate, and therefore to obtain very good X-ray reflectivity data, you have to ensure that there is no scattering in this direction, and this gives rise to a particular condition wherein you have 2 theta f equal to 0. So, essentially this is achieved using, this figure shows a very nice way wherein you increase alpha and alpha f, right, symmetrically to probe the reciprocal space perpendicular to the surface, and while doing that you have to ensure that your 2 theta f is actually 0. so that all the information that we are getting is only along the z. And this is very important because the interference, now why do we get all these speckle pattern that I showed you? This is due to interference between layer and substrate, or if there are multi-layer film, you get interference between different layers, or layer and vacuum if there is only one layer. And this gives rise to an interference pattern like we get during say a Young's double slit experiment, and this leads to a maxima and minima. And this interference pattern can be used, again remember what information we are getting is in reciprocal space, but once we convert it to real space, we do get information about say thickness of the film. So these are known as Casing fringes, and this gives us information about the layer thickness. Having said that, not only for very homogeneous thickness or homogeneous films and we can determine thickness, we can also using a lot of assumptions X-ray reflectivity to analyze roughness as well as interdiffusion profiles in various interfaces. So a schematic or rather a experimental result of GSAX pattern of the cobalt 0.6 nanometer on silica 4.3 nanometer 60 such layers discontinuous multi-layers shows you see it shows Qy equal to 0. Here is Qy, but you see your Qz, you see nice Bragg diffraction peaks corresponding to cobalt. So you can imagine that how you can use. So I am not showing the analysis part over here, but using this you see this is in the reciprocal space. So this will be say something like nanometer inverse. So using this we can actually find out what is the period of the film. Okay. So now let us go and have a look at the instrumentation part. Up till now when we talked about instrumentation of X-rays, I hope you know what all is needed. But having said that, one thing that needs to be remembered, as I had already mentioned, is that for grazing incident small angle X-ray scattering, almost always a synchrotron is needed. And therefore, I am showing a schematic of the grazing incidence small angle X-ray facility with ultra high vacuum chamber at BM32 beamline at the European synchrotron radiation facility. So why do we have a ultra high vacuum chamber? Well, to utilize grazing incident small angle scattering to its optimum. Now, ultra high vacuum chamber actually ensures that we can do a lot of thin film deposition, and that is what is shown over here. So you can do a lot of deposition sources, right, and study the evolution of these nanostructure, be it nanofilm or say quantum dots in situ, and really observe how they are growing, in vacuum. So this assembly essentially shows that from a synchrotron we get a nice coherent parallel ray of beam which is incident on your sample, and you see over here we have a beam stopper, because if there is a direct incident beam it can cause damage to our detector, and you can see the GSAX detector is placed right at very small angle to the incident with respect to the sample. And you see over here we have this normal grazing incidence X-ray diffraction which is at a slightly angle, at a slightly higher angle, but you see the incidence over here for your grazing incidence small angle X-ray scattering is pretty small, and this can be figured out as you see they are almost in the, they are not in the same line, but they make a very small angle with the sample, right. So this shows another the same thing in a different assembly. Again note the distance between your sample and the detector is huge, and there should be a beryllium window over here so that your X-rays can pass, and here you see there is almost normal. You see how small the angle is, right, and you see here you get all the information, in plane information over here straight away on your 2D detector, while out of plane information is over here Q perpendicular, right. This is where you will get your specular pattern and your Yoneda peak. So again I am mentioning time and again that all these information, these are all exaggerated figures, these are all happening at a nanoscopic level, and see this angle is very small, very small, and that is the reason essentially why we keep this distance very large, right, so that we are able to see some difference. Okay. So I hope you appreciate what all is the overall structure of a grazing incidence small angle X-ray scattering system, and therefore these are not available in laboratories and are available on at various beam lines in a synchrotron source. So how do they look like? We talked about form factors and all, form factors as well as the interference factor, right, the interference pattern, right. So, it was rather let us go back and have a look. So, this is your interference function, right. So, we have form factor and we have interference function. So, let us see now how actually they coincide, right. Like this we had seen in case of small angles X-ray scattering, that if the form factor is different, how do we see different diffraction, rather a different scattering pattern. Here, in addition to the different scattering pattern, we also get information about how those different particles or those different dots are assembled in a 2D along the 2D substrate. So, this is what we will try to understand. So, the form factor stuff, we know that if you have a particular shape in real space, how it can get transformed into the reciprocal space. So, this is just a simple Fourier transform of the shape under consideration. So, here if we look in the first figure, we see that if we have a cylindrical shape, we do get a particular pattern. Now, I would like to mention that this takes into account the diffracted wave Born approximation, right, diffracted wave Born approximation, which accounted for different reflection and refraction conditions. So, this diffracted wave Born approximation ensures that this is the kind of pattern that we get. Now, you know that if we are getting this kind of a pattern, a particular kind of pattern, this can be correlated with the shape of the particle, right, and you see there is a bit of periodicity. Now, this periodicity comes in the reciprocal space because of various multiple scattering events, right. Now, if we go and have a spherical shape, we do see that we get a completely different kind of pattern. So, see, depending on the two shapes, right, a cylindrical versus a spherical, we can get different form factors, right, in the reciprocal space. The same case or similar case is shown for a half sphere as well as for a prism. So, here you can see how different it looks, and depending on this particular form factor, we can find out what is the shape of the particles. At the same time, I talked about, right, like how we are keeping the material, the nanoparticles in 2D can give rise to what is known as the interference function. So, therefore, if you look at a simple hexagonal structure of say particles, that means, in other words, if the particles are arranged forming a hexagonal lattice, we get the variation in along say something like your alpha f and 2 theta f in this pattern. So, you do get these fringes. Now, these fringes that we are getting have a particular periodicity because of the hexagonal structure. Now, the actual scattering pattern that we are going to get is going to be the superposition of this interference function and the form factor, right. Like we had this equation f of q y q z square into s, right, that was your scattering intensity. So, this is where you see. So, if I have a hexagonal arrangement of my spherical patterns, well, I do get a pattern which corresponded to my spherical form factor, right, like which we had derived over here. So, here we have a spherical form factor, but the way it is arranged, the lattice is hexagonal. So, therefore, there is a superposition of these two things and we do get a very different pattern, right. So, now this form factor, I hope you appreciate that once you get your experimental pattern, what we need to do is we need to assume shapes or make a first guess, do simulations and get a good match between the experimental and simulated pattern to comment something about the size and shape of the particle. Similar information or similar patterns for now, can we try to guess what exactly we are getting? So, I hope you appreciate that we are getting the same period, or rather it is the same period. So, this has to be all hexagonal. Now, if you look at this one, now this to me looks like, so this is what? This is superposition of half sphere with the hexagonal one, while this is superposition of half sphere, the superposition of a prism with the hexagonal lattice. So, therefore, I hope you appreciate that for the last two scattering patterns, particularly for the we are having a hexagonal arrangement, however, of particles. However, for the first case, we are having a half sphere or rather a half sphere sitting at all the corners of the hexagon, while for the second case, which is shown over here, we have a prism sitting at all the corners of the hexagon. So, here again I have chosen one particular example and try to show you how exactly we can see in situ growth of particles. So, here again we are having the growth of germanium on silicon 001 substrate, right. So, here you see that as the sample or as the quantum dot is growing, we do see that there is a change in the scattering pattern, and also all these things can be confirmed by doing say AFM or scanning electron microscopy. So, we can see that with the deposition condition we can look at how the how the quantum dot is evolving in shape as well as size. Now, I would like to emphasize that for carrying out SEM and all, it is very difficult. You cannot do it. We have to stop at each and every stage and then do the sample. However, grazing incident small angle X-ray scattering probably offers the only technique wherein you can monitor the evolution of a particular the growth of particles or catalysis or chemical reactions occurring at the surface in situ, right. So, this is the only technique that gives you real in situ information. Okay. So, to summarize, I hope you appreciate that grazing incidence small angle X-ray scattering technique is now well established to characterize morphology of nanoscopic and to a certain extent microscopic particles. For microscopic particles, we essentially do not really need grazing incident small angle X-ray scattering, but for nanoscopic particles, this is probably the only technique to give you a lot of information while doing in situ experiments. We get complete information about nanoparticle sizes, shapes, distribution, faceting as well as spatial correlation. However, I would like to point out that this information is not a straightforward information. Like diffraction, all the information that we are getting is in the diffracted space, and that corresponds to the Fourier space, right. The best possibility of GSACs is the in situ studies. They offer an excellent platform to study growth, catalysis and self-organization. Having said that, synchrotron radiation is almost necessary. I will make a very strong statement and say that synchrotron radiation is necessary for doing good quality grazing incidence small angle X-ray scattering, and having done grazing incidence small angle X-ray scattering, it is always a good idea to confirm your results with say other techniques like scanning electron microscopy or scanning tunneling microscopy or AFM. Having said that, grazing incidence small angle X-ray scattering, though not available routinely, offers a very sophisticated tool to study the structure of materials at the nanoscopic scale. Thank you.